Hi, welcome to this Introduction to PMBus presentation. My name is Chris Ammon, a member of Avnet's technical marketing team, and today we're going to be talking about what is the PMBus and what it can do for you in your designs. So what is PMBus? PMBus is a digital communication bus standard for power IC devices. The physical design interface is an I2C. It enables things like programming, controlling, and monitoring your different power devices in your system. You can see from the block diagram, you'll typically have a system controller which can configure and control each of the different power devices, and you can also monitor their activity and performance from the system control device. It's an open standard, not supplier specific. It's owned by the System Management Interface Forum. The specification is free and it's free to use. You can access it from the web link here. It's important to note that it's not a power supply standard. What I mean by that is it doesn't have a required topology, form factor, pinout, anything like that. It is simply a standard communication interface that can be used with a large variety of different power ICs. Another thing to note is that it does not support converter to converter communication. Communication structure is such that you have a system control that can talk to all the different PMBus devices, but the PMBus devices cannot talk to each other directly. So some of the basic requirements of the PMBus: devices must start up safely without bus communication. They must be usable with or without a system manager or controller. They have to support one-time programming, meaning it's programmed once and you never have to touch it again. And when it first comes up, it has to default either from non-volatile memory or from pin programming. What that means is devices must come up in a known state. So basically these things just ensure that if you power up the device without having loaded anything into it, you know what it's going to power up as. Depending on the device, depending on the manufacturer, this is not always universal. Some parts will come up to a pre-programmed output voltage without external programming. Some have external pins that you program the initial voltage with. So it's important to look specifically at the device you're planning on using and then design accordingly. Must be able to be used with or without the system manager controller. Basically, this means that just because it is PMBus, it doesn't mean that it has to be maintained or monitored by a system manager. You can just program these devices once during manufacturing and not even set up onboard communication and never have to worry about them again. It's there as a feature that you can use, but you don't have to use it. The support for one-time programming, again, it has to support being programmed once, say during manufacturing, and never having to be touched again. So those are some of the basic requirements for the PMBus interface. Some highlights of the PMBus: using in-system communication allows you to configure and control your rails. You can margin supplies up or down, you can turn supplies on or off. It allows you to monitor for fault conditions. And not only can you monitor it, but obviously from the system control, you can create different actions based on certain fault conditions. So you can configure your over voltage, your over current, temperature. You can set those thresholds, and then based on what you want to do in those situations, you can then design your system so that you can either turn these off, take some kind of action, and really use the information gathered from the power devices to gain more control of your system. Again, you can see here the system control communicates over an I2C physical interface. This could be connected back to a header that connects to an external dongle that you plug into a PC to talk to it. It could be straight from an FPGA, an MCU, anything like that. And again, you can configure and control the devices from the system controller and then monitor what these devices are doing while your system is operating. So again, fault monitoring could be used to alert the user. You could turn things off, turn on or off interfaces based on these faults, record them for reliability information, things like that. This technology has been used for a long time in computer hardware, things like that, but has been fairly cost prohibitive in more wide applications. However, with advances in technology and the more widespread use, the cost points on a lot of these devices has come down to where it actually looks to be a viable solution in a lot more different applications. A little bit about the governing body of this standard. Again, it's the System Management Interface Forum. Not only do they manage the PMBus standard, but they also have a standard for system management as well as battery system interface controls. So specifically here, we're interested in the PMBus standard, but you can see this group specializes in different system management type interface communications. For more information specifically on the PMBus, you can go to the pmbus.org website. There's a great presentation posted on the About tab with an introduction to PMBus, which goes deeper into some of the addressing issues and some of the actual software features of the PMBus that we're not really going to discuss here. This is more of an introduction into what it can do for you, but I highly recommend checking out this presentation as well. Again, it'll give you more insight into the actual software workings of the interface. The latest specifications are available under the Specifications tab. Another thing to note is that it's important to know that not all devices you look at will support all features. The specification defines how features work if they're included, but that doesn't mean that every device you look at will include all features. So what that allows you to do is you can have devices that maybe aren't as feature rich as some other ones to control cost, but still give you your basic functionality of being able to margin supplies, set fault conditions, things like that. So just know that just because it's PMBus doesn't mean that it has all the capability of the entire PMBus standard included in that device. So with that, we're going to take a look at a specific example of PMBus implementation, specifically here with our Xilinx UltraScale newly released design platform. On this board, we use the PMBus capable devices to power this system. Again, you can access it from an external dongle, program it once, and then if you don't want to, you never have to use it again. However, some of the things I'm going to show you, you can use the dongle and the GUI to allow monitoring of the voltage, current, and temperature of these different devices. You can also connect to the FPGA to allow in-system monitoring, as we mentioned earlier. So with that, we're going to actually go through the GUI and look at some of these different things so I can show you some more of the features that are available to you in this GUI. So here's our UltraScale board. Now the first time you power up this board, the devices, before they're programmed, default to come up at 0.5 volts. Now in a lot of applications that's not going to be a problem because it's typically going to be too low for any of the devices to try to start up. But for safety and for our startup procedure, we provided this 2-pin header right here that you can short to ground, which will disable all of the outputs on all the regulators. So the first thing we do, the first time we powered up this board, is to disable all the regulators. Then we take our I2C to USB hardware dongle, plug that in, and then we plug this dongle into our computer. So now we'll be able to communicate with all the devices while their outputs remain off. This will also let us program the devices so that the next time we power up the board, you can see that they're all programmed. Now in this particular board, I've already programmed all the outputs, so what you would do after you program it is you would power down the board is already powered down, and the next time you power up the board with the jumper removed, you'll see all the supplies come up as they should. Just to show you, if you keep that jumper on, all the outputs are still disabled. So since this board has already been programmed, what we'll do now is actually look at the GUI itself so you can look at the information that's returned to the screen while monitoring this board while it's powered up. So here's what the GUI looks like after you've connected it and powered up the board. Now one thing to note before we move on is that with the particular procedure for this board and with these devices, that's not going to be universal. Again, Depending on the manufacturer, depending on how they've implemented their graphical interface, their default startup conditions, it's going to vary. So make sure you verify with the particular setup that you're using how the boards come up for the first time and how you go about programming them and communicating with them after that. So with this board, this is the IR Power Center GUI. You can see that we're communicating now on the bus. You can see the different voltages, 1.8 volt supplies, 1.2 volt supplies, a 1 volt supply, and a 0.95 volt supply. You can see the current consumption on each of the rails. Some of these are at or close to zero, which is expected because the board isn't running anything intensive right now. And you can also see the temperature of each of the ICs. Now over on the right, you'll see that each device is broken out individually. You can see the different hardware addresses and the PMBus addresses. Using this GUI, you can create board designs that will then assign properties to each one of these devices. Now, I just loaded the profile that I've created for this particular board. What you'll notice is now these names here are no longer generic. I was able to go in and change this name. Doing the edit text address, you can go in and you can change the name of this address to reflect what you actually have assigned to that particular device. So now with all of these devices populated, you can see which board or which device is going to which command, and in this main window you can monitor each one of these. So if we look at one of these individually, I'm going to reload that profile so that they're all named accordingly. So if we look at each one of these individually, what we'll see is a list of the basic commands available using the PMBus for this particular device. Now, this isn't all of the commands that this device is capable of, but this is a subset of those, the most important ones, just to kind of get you familiar with it. What you can also do is change this to all commands. All commands will now tell you all of the different codes, command, operation, and all the values that you can change for this particular device. Now, if you wanted to change one of these, what you can do is you can come over here to the command drop down and look at your specific criteria that you want to change. So let's say we want to change the overcurrent fault limit for the output. You can come in here, change this to whatever current level you want, and write it to the device, and then it will be saved. And from that point on, that will trigger the fault event for your particular design. So there's a lot of capability. You can go in and you can change this for each of these devices so that you can do it individually, depending on the rail, depending on what you're running on that supply. It gives you a lot of flexibility into creating these different fault conditions and then designing around that based on how you want your system to react to those fault conditions. When you click on the device themselves here, you can go in and you can load configuration files or save them. So this is how I went and programmed each one of these devices the first time. I would go in and change all the parameters that I wanted to change. Then I would go to the device itself and save that configuration file. And after I saved it, when I plugged in the next board, I was able to load that configuration file, program the part, and have it come up with all the same values that I assigned here. So very simple, very easy to use. The fact that it comes up with basic commands first and then you can go to the all commands was done really just to kind of give you a subset of what was important, and you can go in and experiment with all these things as you become more comfortable with the interface. Now, one of the nice things that I discovered through actual real-world scenarios is that you can see the current consumption on these devices as well as the temperature of the different devices. While you're running code, while you're running your design, you can actually leave this window open and monitor real time what the current looks like, what the voltages look like, what the temperature rises look like, and it can potentially alert you to possible problems with your design. One thing in particular that I noticed was that in certain conditions with certain bit streams loaded in the FPGA, this current consumption on the core rail continued to climb. Well, what I was running, it didn't really have anything additive going on, which led me to believe that we may have thermal issues with that particular design, which would be indicative of us possibly needing a heatsink for an application running this type of design. So things like that, abnormal current increases can point to thermal issues, things like that. It's a nice thing to have, especially when you're in your initial board bring up debugging phase. Now keep in mind, all the things that you can access through this GUI, you can also access real time through this I2C bus on the board itself. So whether it's a microcontroller, an FPGA, if you build in the code to monitor these, talk to this device, you can create actions based on the fault conditions that may be thrown by the various devices, and really keep track of exactly what's going on from a power standpoint inside your system. So again, here's our block diagram for the power architecture that's used on the UltraScale platform that we've been reviewing. Again, it gives you a lot of capability. The ability to monitor real time what's going on in the system is really handy, especially if you have some designs that you're not exactly sure why they're behaving the way they are. Maybe watching the power profile can give you some insight into potentially what may be incorrect in the system. Specific to the IR38060 device, again, it's PMBus interface, obviously. You've got that full programmability for the voltage, ramp time, sequencing, and a lot more. I definitely encourage you to download the data sheet, check out all the features that are available in this device. This particular device has a 0.5% accurate reference, which is really good for your overall output accuracy. It also has remote sensing. Remote sensing is very handy to have, especially with tight tolerances. It samples the voltage at your intended load and can make adjustments to the regulator output to make sure you maintain a certain level of accuracy at your intended load. The easy-to-use GUI for monitoring and programming, again, you can use it not only just to initially program these devices, but you can also connect that dongle and monitor your power supplies while you're actually operating different things in the system. You also have that capability to monitor in-system. You just have to develop the code to read and communicate with that bus. Custom part numbers can be created for this, so that if you've created profiles specifically for what you need, you can start with a base 38060 part number, add a special suffix to it, and have parts delivered pre-programmed with your profile already in place. In that case, you don't even have to program it the first time. You can order these parts and have them ready to go when they arrive on your board. It's a relatively low-cost platform. The cost for this particular device is right in line with a traditional DC to DC converter. So it's definitely, as I mentioned, that the way the prices have come down for this type of technology makes it really competitive and very interesting to look at, just because of the power and capability you gain by adding this interface to your board. Call to action. From here, I'd really like you to download the PMBus introduction presentation that I mentioned that's available on the pmbus.org website. It goes into a lot more detail about how this specific standard addresses some of the shortcomings of an I2C interface as far as addressing fault handling, things like that. Very interesting, but a little bit deeper than I wanted to go for this introductory presentation. Learn more about our Kintex UltraScale platform. You can access that from the web link here. Learn more about the IRF38006 family. In addition to the 6.0, there are other devices in this family that also have the PMBus capability for higher current levels. Very interesting family of devices, and as I said, very cost competitive, which makes it very attractive for a wide variety of applications. And finally, contact your local FAE if you have any further questions, would like to see a demonstration of this technology, or if we can help you with anything else. Thank you for your time today, and I hope you found the information useful.